there's a Sesame Street episode where Cookie Monster has a plate with 4 cookies, and the people keep coming and taking his cookies. And he's sad that he's left with 0 cookies. But Annette Bening is on the show, and then she tells Cookie Monster, 0 is a number. You can have 0 cookies. And Cookie Monster's happy, and then he eats a plate.
No, that is bothering me now.
I'm just more upset that I didn't understand.
Okay.
How my friend was somehow.
So, for the most part, I graded the first exam. There were a couple that were taken outside of the class, so I need to get those and grade those. And there was a few students who just left a problem blank at the end, and that, so I've given some opportunity to recover a few of those points. And so that affected people differently. But anyway, they should be graded and back on Friday for that. Many students did very well in terms of many concepts and problems. So, but we'll get more of a full report with solutions and everything once I have all the papers and I can give back to everybody. Okay? And so what we're going to continue on today is continuous random variables. We've looked at a couple of times on this. There will be a homework 5 due this. It's not realistic to have it due Friday, so kind of that's the schedule. We'll have it due Monday. Get it posted soon, so that you can do Monday after this on some of these continuous random variables. Right? We've looked at continuous random variables in kind of a general case. If X is our random variable, the probability densities that are continuous, they can have a probability density function. They can have a cumulative distribution function. If you look at the probability that it's less than or equal to X, we can use these things to calculate probabilities of certain outcomes, certain ranges. We could take the expectation of continuous random variables as an integral of our X value times its density, right? And do a few other things. Right? We looked at a couple specific examples. Right? We looked at some examples. 2 specific things that we looked at was an exponential random variable, right? Which is a positive random variable. I guess I can get it on here. One example we looked at was exponential, where there was some parameter mu, some factor that influenced the shape of the distribution and the probabilities. It showed up in the density as mu times e to the negative mu x. Mu is a number greater than 0. This density was on the positive real numbers, right there. And the density was 0, technically, for other places. So this graph of the probability density was a decreasing function. And so the probability we would be, say, less than some point here, right, would be the area under that curve, under that, or the probability would be bigger than that, would be the area above. For the exponential, we figured out how to express that by taking an integral. So I'll give a second for people to get that down. That's one example. So for this exponential, the probability, the cumulative distribution function, the probability that we're less than or equal to some value was an integral from 0 up to x of this density. I'll put a little, we switched to t in there as a technical aspect, just doing the integral, because if x is up at top, we don't necessarily want to have x down in there. But it ended up being a certain function. So the probability that x is less than a certain number is that. The probability that x is greater than some point is 1 minus that probability. So it ends up being e to the negative lambda t. And this cumulative distribution function, as x is changing, gives a chance, oops, that should be x here, not t, sorry about that. And we also looked at that the expected value, the average value of the x values that we're going to get turns out to be 1 over lambda. Well, not lambda. I was using u before. Sorry about that. Different books use different. So if this is, if I said it's exponential with a parameter here, mu, u goes in there instead of that different Greek letter. So kind of the average time, this exponential was often used for waiting times. How long does it take something to happen? And the larger this is, influence how concentrated you are near 0, how rapidly the things happen. Right? So that if you have a big value of mu, things happen rapidly. And the chance that you're bigger than a value becomes quite small for big values of mu there. But if something rarely happens and it's sparse and this mu is very small, you might have to wait a long time for the chance for things to really happen. So we looked at that as kind of as an example. What we want to do today is look at a new example. Right? The new example is the normal distribution. Many times when we measure things, right, the type of outcomes we have are kind of symmetrically distributed about their average. They're concentrated toward the middle with a smaller chance of being more extreme. And the density is going to look something like the familiar bell-shaped curve. The probability density function for a normal is that bell-shaped curve. Right? The bell-shaped curve for a normal is centered around the average, so mu is going to be the expected value of the random variable. Here are the different values that x can take on. Right? And how spread out it is controlled by a variance. Sigma squared is the variance of x, or sigma is just the square root of that, standard deviation of x. And for a normal curve, as we'll see, going up about 2 standard deviations is most of the area. And this particular density has a mathematical expression, but it's a little bit less useful to us. Mostly we will evaluate that in tables. Right? So things like scores on exams for a generally randomly sampled population, heights of people for a random sample of a population. You could very well get distributional shapes that are normal. So the handout gives a little more description along with this, right? So in general, a probability density function is some curve, and the area under the entire curve is 1. And area is defined by the area under the curve. So if there's 0.4 to the left over here and 0.6 up there, those would be the probabilities. If you have area between a couple points, pick a couple points, the area in between is going to be a probability. Right? And expectation kind of gives the balance point in this range that's going to support that. And standard deviation describes kind of the spread over those values. And the specific case that we're going to look at is this normal distribution. Normal, yes.
We didn't get, oh.
Oh,
I'm sorry, that was my bad.
Oh, sorry.
I thought it was, you handed out the papers.
No
I'm
problem.
sorry, Ian.
Oh, no worries.
I never
Just
looked
said,
at it.
I think other people have that.
Great, no problem, right? So it generally has this shape. The density is defined from negative infinity to positive. That's extra ones? Sure. Oh, thank you. It's symmetric about the mean. The default case, called kind of the standard normal, has a mean of 0 and variance of 1. Half the observations are to the left, so 50% is to the left. So 50% is to the right. Right? The median is the mean in this standard case is 0. Right? About 68% of the area is plus or minus 1 standard deviation. About 95% is about plus or minus 2 standard deviations. And almost, nearly all of it, 99.7% is plus or minus 3. So you can have things under normal that go out farther than that, but they're relatively rare. Right? The general case, because when you're really doing something, you're measuring something, there's a scale to it. You're doing it on a test score scale or a weight scale, right? Then there's a mean and a standard deviation. And the nice thing about the normal is that the shape and the areas remain the same if you convert it to standard deviation units. Right? So if you're one above, probability of being one above under a standard normal is the same probability that one of these normals with an arbitrary mean and standard deviation is one above. So plus or minus 1, plus or minus 2, plus or minus 3 should have exactly the same breakdowns in terms of the probabilities as the standard normal, thinking of it as how many standard deviations you are away from that. Right? And what we'll use to calculate probability, we can calculate probabilities because the cutoff points of the normal distribution have been tabulated. They're presented often in tables like the one that's here, right? And this table is actually in the front pages of our book. It's in the front cover, and it's also later in the appendices. But it's also included in things like the R statistical program. Right? So, just as an example, the Haynes was a health and nutrition examination survey, right? A national survey of health in the United States. And it interviewed men and women, collected data on children as well. But of the women aged 18 to 74, in that study, the average height is reported as 63.5 inches. Standard deviation is reported as 2.5 inches. And we can ask questions such as, what's the probability that a woman that you would pick from this study is more than 68.5 inches? So that's 5 feet, 8.5 inches, or taller. Right? The chance that a woman would be exactly 68.5, we don't really ask under a normal distribution because it's continuous, and we're going to ask about areas and intervals. So to do any of these calculations in a normal, we're going to convert it to the standard units. Right? We're going to subtract the mean, divide by the standard deviation. So this is 68.5 is chosen. I chose it in this example because it's 2 standard deviations above. Right? So 95% of the observations are plus or minus 2 standard deviations approximately. Right? So that means that, picture in this one. So in our example, here in Haynes, here's the 63.5 average. This is how many inches tall a woman is, and we're interested in here up to 68.5. Well, on a kind of standardized scale, if this is 0, and it's 2.5, standard deviation is 2.5. This is 2 standard deviations above. In figuring out normal probabilities, we'll use that the total area is 1, that it's symmetric, about there. So this one fact, that there's, so 2 going down 2 standard deviations is 58.5. Right? So here, the mean is stated as 63.5, the standard deviation is 2.5.
So like, did you just pull that number out, or did you figure that out via the formula?
Based on the survey data.
Okay, so
right?
they
Just
said-
given those,
okay.
those 2 numbers. Right? And if about 95% of the area is between plus or minus 2, right? And we want to find out what the chance that a woman is greater than 68.5 inches in height. You usually do these things by a little bit of reasoning about the areas. Right? So if 95% is plus or minus 2, what percent is outside?
5%.
5% should be outside, and so 5% greater than or equal to 2, or less than or equal to -2. Right? So if it's symmetric, and there's kind of an equal chance of being above a point or below the negative of that, right? And so how much area should be up here? Right? If it's 5% for these 2 shaded areas, then the chance that you're in half of that, right, is going to be the 2.5%. Oops. So the probability that our random variable, that a standard normal, v, right, is greater than or equal to 2, is about 2.5%. Right? This is going to be the same answer as the probability that is asking in terms of the actual heights is greater than or equal to 68.5, right, in this case. So that's the nature of getting some probabilities within this, right? 2 is a special value because it has this. But really we can do this with any other value we want in our, based on using the more detailed tables. So as a second example, say you randomly pick a woman, what's the chance that the woman is between 60 to 67 inches tall? We have a picture here. Here's the 63.5 in terms of our inches. And now we're going to ask 68 was out here at 2 standard deviations. So it's going to be somewhat less than that. So here's 67. I've chosen equal distances from these 2 things as this example. There's no reason you necessarily have to do that. So what we're going to ask is, what's the chance that the woman is between these 2 is going to be the area under the curve there. So we don't get a table for every normal, but so we're going to convert these to the standard units. We're going to convert these to the upper one at 67 minus the mean of 63.5 is divided by the standard deviation. That turns out to be 1.4. We're also going to calculate the lower endpoint, right? 60 minus 63.5 over 2.5. That's an equal distance below. This one turns out to be negative 1.4. So on the z scale, or the standard scale, that's centered at 0, what's the chance we're between 1.4 standard deviations below up to 1 standard deviations above? So what's the probability that negative 1.4 is less than or equal to z is less than or equal to 1.4, right? So to get more precise probabilities for this type of thing, right, one place that we can look is the table, right? So let's take a look at the table that's provided. Here this is. Right, so standard normal curve areas. The probability that Z is capital Z, standard normal is less than a value. This fancy phi here is the cumulative function for a standard normal. It's a special symbol that's just used for that one. We don't need to be sort of formal about it, but so you know that when you read that, that means just the probability, the cumulative distribution function for a standard normal. This is the standard normal density curve, and the shaded area that this is going to give below a value of Z is this all the way over here. I think in the book it shows up as shaded, but when I copied it, scanned it, it didn't show up again. And so for every value of Z here, we want a probability. So the way they represent that in this is you get negative 3.4, negative 3.3, negative 3.2, and so on. And then they add one more decimal place by putting additional decimal places on here, right? So negative 3.40, negative 3.41, negative 3.42, and so on. They add extra decimal places on there. And so the number that we're interested in is a Z value of negative 1.4, right? Is one of them. So Z for us that we're interested in negative 1.4. Well, so here's the 1.4 part over here. And so it's really 1.40 to two decimal places. So the first column here is the 0.00, right? Nothing else in the there, so move that around. Right? And it gives this number as a probability here. Right? So the probability you're less than or equal to negative 1.4 is 0.808. That's not exactly what we wanted, but let's write it down for now. So the probability that Z right, is less than or equal to negative 1.4 is 0.0808. That's something you can write down basically. Now in this picture, that's that area in there. Once we look up that number, what else do we know? That flip side, right? The chance that you're bigger than 1.4 is also 0.0808, right? So symmetry gives us that, right? So what's the answer? What's the middle?
1 minus.
1 minus goes to this, right? So this probability is 1 minus 0.0808, 0.0808, and 83844, right? To that. For this, let's also look up the 1.4, right? On the second half of the table. Now, on page 2, it also gives you the positive areas. Some books only give you half. They maybe only give you the positive ones. But here's 1.4. Right, that's we're looking under the Z values of 1.4 there. So the probability that Z is less than or equal to 1.4, and with the 0 there for the second decimal, right? The 0 zeros give us this one, is 0.9192. So looking at, that other piece of information from the table, the chance that a standard normal is less than 1.4 right, is 0.9192. So in this picture, the chance that you're less than or equal to this is bigger than 0.5 because you're across 0. Right? The probability you're less than this point was 0.9192. And so But of course, that's too much. That's not really our question. We want to be in this interval. So one approach to doing this is to calculate the probability you're less than 1.4 and then subtract out that little piece there. So the probability here could also be written as the 0.9192, right, minus the area that was over here, which is 0.0808. So the probability that z is less than or equal to 1.4 minus the probability that it's less than or equal to negative 1.4. And you get that area. So about 80%, about 84% of the women, if this normal distribution really describes the distribution of heights, would be between 60 and 67 inches. But any questions about it? So for the other questions, you follow much the same format. So less than 68 inches. And it can be less than or less than 58 inches. 58 minus the 63.5 over 2.5 is the z-score. By subtract the mean, divide by the standard deviation. Right. And that's negative 2.2. Right. And so the probability that a standard normal is less than negative 2.2. So if we look that up on the table, what number do we get as a probability?
0.0139.
See that one there? 0.01339. That's that area. Now, if you had another number, so let's see. If you, so if it had been, say, 59.25, 63.5 over 2.5. So that's not really what I want to do. Anyway, we'll just go leave it like that. But so if you happen to get another number, like if this had been a little bit, bigger, it would have been, negative 2.2 and a little bit more, right? So if it had been a little bit more and you needed something like the probability that z is less than negative 2.26, say, just as to illustrate the looking up on the table, right? That's a little bit further away from 0. It's a little further down, right? So it's going to be smaller. Right? So but then you would look at the negative 2.2 row, but then go over to the 0.06 column, right, to get that one. So what number is there? Do you see a number? Yes.
0.0119.
0.0119. So if you go across that row, let's have a straight edge to see some of those. To get that second decimal place, then you go to the 0.06 column. And that would be that probability. It's a little bit less if it was a little further away. So there's two transformations that are really possible. We've used one. So if x has a normal distribution with some mean and standard deviation, different places will either put a sigma or a sigma squared here. They either talk about it in terms of standard deviation or variance. I like to talk about it in terms of standard deviation because standard deviation is on the same scale as the mean, but you always have to watch to see what they're doing. Also, the computer programs usually want standard deviation, so keep track of that. And then you subtract the mean and divide by the standard deviation. This new random variable is our standard normal, and that's the one we get from all the tables. Right? taking this other way, we start with z is normal 0, 1, the standard normal with mean 0, variance 1, right? And we undo this transformation, right? So we solve for x. If we multiply by sigma, we get sigma times z, and we add mu to both sides, we get mu plus this. It turns out that x is a normal distribution on the scale where we would measure some application with a mean mu and a standard deviation sigma. So if we can look up things like percentiles of a standard normal, and we have a mean and standard deviation in mind for the thing we're measuring, right, then we can transform the percentiles to the other scale. Right? So let's think about an example where we do that. Any questions on that? So in the second example that's on there, say that a certain group of tax forms classified by wage earners in certain industries, let's say the average income is $47,000 with a standard deviation of 10,000. And assume incomes that this is coming from, the subset of income returns, is approximately normal. Approximately normally distributed. We're going to jump down a couple of questions. What's the 75th percentile of income? So to do this, to find the percentiles, we're going to look at the standard normal, right, and find the 75th percentile of that. Right? What is the standard normal z? Right? So to do that, we can look at the table. Right? So z values are on the outside edges and probabilities are in the middle, like cumulative probability. So we want to find the cumulative probability that's about 75%. So can you search through these pages here and find the place that is going to be the 70th percentile, the 75th percentile?
It'll be around 0.7, between 0.6 and 0.7.
Yeah, between 0.6 and 0.7 it will be.
0.6, 7,
0.67, 0.68. 0.67, 0.68.
Yeah.
So the 0.606 is 0.067. There is, what, 7486? So the probability that z is less than or equal to 0.67 is 0.7, what is it again? 7486. And the probability that z is less than or equal to 0.68. A little bit more than that, 7517. Right? So it's somewhere in the middle of those. It's actually 0.6745 is closer to what it is. If you just took the midpoint there, 0.675, and said that's about what it is, for kind of a rough approximation would be okay. We can't use a computer. If you use a computer, it's a little bit closer. Right? So that's on the standard normal scale. Right? We got to transform it back to the scale of incomes. Right? So we're going to multiply that number. I'm going to use this one. The average was 47,000, it said. And we're going to, the standard deviation is 10,000, so you multiply that by 6745. And and you'll get 47,000 plus the 6,000 some, so it's 53,745 dollars. So that would be the 75th percentile for income according to this distribution. So this was the average, and this is the standard deviation, and that's how it would scale up.
So
Yep.
why isn't it just, the 75th percentile is plus, I thought was just plus the 10%, like plus one standard deviation away from the mean to get
So-
to the first, second, third, fourth quartile.
So the going a whole standard deviation actually, under the normal, includes a little bit more. So yeah, so if we go up to 1, this would be a higher probability. The probability that a standard normal is less than or equal to 1, if you look up 1.0 on here, is about 0.8413. So a little bit more. Right? So if you took $57,000, that's about the 84th percentile. Right? Because the probability of your one standard deviation is, so it's a little bit more. Yeah. The normal is a little bit more concentrated. Okay. How about the 25th percentile?
That would just be, times 10,000, 1 minus this 0.6745, or is that 9?
Close, close. That's the nature of the idea, right? So to get the point that has 25% below is like having 75% above. So if we have a picture here for a standard normal, and here is 0, and 0.675 approximately has 75% below, right? This one has 25% above. Right? And now we're looking for the point down here somewhere that has 25% above it. Right? So by symmetry, it's the negative of that. Right? So negative 0.675. One thing that's tricky in this example is everything's kind of decimals, right? 0.675 here is actually a z-value, right? Rather than a percentage, right? If the z-values are 2.2 or 1.6 or something, it's clearly that they're not probabilities. But when it's a decimal like that, it kind of confuses the issue anyway. But the probability that, well, z was less than or equal to 0.675 was about 75%. The chance that it's less than or equal to negative 0.675, right, is the 25%. And so our x value for the 25th percentile is our 47,000 average, plus now 10,000, but our z value is now negative. And so we subtract that amount, and we're at 40,255 dollars. Yeah. So the symmetries are very useful for doing this. Transforming everything to the standard scale back and forth. And so you can ask a lot of different questions. So just as to emphasize a point, so say if you're looking at verbal SAT scores, and I tell you the average is 580, and the standard deviation is 70. Can you draw and assuming that it's normally distributed, as the shape of the probability distribution? Now, I know that the SAT score just on integers, but there's quite a few integers, right? Fairly, a lot of different places, right? Can you draw a graph that would represent this probability distribution? How would you draw it? I'll go ahead and draw the bell-shaped curve. I like drawing them starting kind of from the top and going down, trying to make it symmetric. Adjust a little bit. What else, and other information do you want to put on a graph? Mean, right. Average about 580, should be here, pretty close to the center. How do you want to depict the standard deviation?
Just do 2 standard deviations in either direction.
To do 2 in say either direction, kind of over here to where it starts to peter out, and there's not much left, right?
So it's 510 to 720, or 620?
Yeah, so if you go up here, if you add 70, then add another 70, 720, it goes up to there. 3, you could put up, 790 gets out here where it's a little more higher, more rare, right? 510 and 440, and then out here where it's a little bit, less likely, right? Could be like 370. So you could either represent a plus or minus a couple standard deviations, or plus or minus 3 at the extremes. Now, the normal goes on forever, right? So the theoretical one, the normal curve, would go below 300 or 200 or whatever the lower limit is, and it would go above 800 or whatever that limit is. But if the probability of getting at 800 or above is really quite small, then it's not going to be too terribly inaccurate. Right? You just kind of truncate it up there. So it still might work for most parts as a model, maybe not as super well for at the very extremes where the truncation kind of happens. But for most things, it can give a pretty rough idea of chances of being in different intervals or percentile, things like that. So it could still be reasonable. Right? But that's normal, right? In part. There's another way to do some of these calculations is in R. Right? R gives you some capacity. And I told myself I was going to start RStudio before, but didn't remember to do it. So the next example on there has about birth weights, right? And says the average birth weight in term births, so births at 37 weeks or beyond, is about 7.5 pounds with standard deviation about 1.2, right? There are different functions for the normal. There's normal distributions. There's 4. One gives you random numbers, right? Where it gives the mean and standard deviations are the default. Right? So say you had 3 children you're having 3 children are being born, and they're randomly sampled from this distribution, right? What would 3 weights actually look like? Well, one thing with random numbers that I'll mention is you can set random number seeds, right, to kind of control the random number process. So to generate, I'll just put in this, so 0220, right? So what is that? That's 2019, 02 with February 20. So it's a big integer. Just put some number in there, right? You can choose your birth date or some other date. When I'm doing these things, sometimes I just choose the current date. When I've had projects where I have to generate random samples that can be replicated, I kind of choose just the date that it's on. That seems like a fair choice as anything. Now if I type random normal, and let's say 3 children, and the mean was supposed to be 7.5 pounds and a standard deviation of 1.2, this is going to give me 3 values. Kind of around that number, right? With some variability. And if I do it again, I get 3 more children coming in. Oh, one was there at 9 pounds, a little heavier, or a little bit less. Right? That random number seed thing there, if I click that again, and I do the same random command, right, it gives me the same numbers back. So if I ever needed to replicate something or be able to repeat something, right, if I ask you to do an assignment, if I give you a random number seed and you all put in the same random number seed, then everybody should get the same answer. Right? But anyway, right.
So what is that set seed again? How does that affect everything?
So within the computer, there's an algorithm for generating these random numbers. Right? The numbers that it initially generates are just uniform 0, 1 numbers, right? And then it transforms them into normals through an algorithm. But that algorithm for generating a random number has to start someplace. And so if you tell it to start at the same place, you get the same sequence going forward. Right? It looks random as far as we can tell. It's, it would pass tests like you have equal proportions of numbers 0 to 0.1, 0.1 to 0.2, and things, things like that. It wouldn't seem to repeat for a very, very, very long time. Numbers. Yeah.
Do you know which pseudo-random it uses, like the Mercer Twister, or just out of curiosity?
Yeah, there's different names for these, but if you look up under this, it probably down here gives you some details. There's a book that it refs, so there's other things that you could click in there that might tell you a little bit more details about what it's doing. I'm not sure off the top.
I know there's a few different.
There's a few different ones, yes. Yep.
So if you start at that seed,
Yeah.
and you run your R-norm, it gives you the same 3 values. If you continued and ran R-norm again, you get the same, so it keeps doing the same thing over.
Yeah, it keeps going for a while, yeah. If you change the random number seed, it'll start to be completely different in an unpredictable way.
So it's not just a one-liner, it gives you a whole set of data that's going to.
Yeah, so it remembers the place that you started, and then everything you do after that goes in a certain order. If you go back to that beginning and run that long sequence of things again, it all comes out the same. So you could generate, a million different random numbers for an enormous simulation. As long as that you start at the same random number seed, you get exactly the same thing over millions and millions of times. So, right. But if you did a histogram, say instead of taking 3, say you took 30,000 children, 7.5 and 1.2, right? The distribution is going to look roughly normal, right? Because here's a sample from a normal. It's going to be around here at 7.5, and then plus or minus a couple standard deviations is most of the thing. As you take bigger and bigger samples, the chance that you're going to get one extreme observation that's going to be more than 3 standard deviations away increases, right? So if I took 30 million, there's going to be some that are out there that are 3, maybe even 4 standard deviations away, because rare events do happen, by chance. Right? So these other probabilities under there that are with help here. This the P norm is the cumulative probability one, right? So you put in some number and lower, and the things, if it's given a value here, it is default. So you don't have to tell it to look at the lower tail like you would for a cumulative. You can tell it to look at the upper tail. Right? And there's some log, putting on a log scale. Mostly, so what's the probability that a baby born at term is less than 9 pounds? Right? So if you put 9 in here, and then tell it the mean and the standard deviation, right? It'll calculate that the probability is 0.894, about 89%. Right? We can do that if we calculate the z-score, z minus 9 minus 7.5 or 1.2, that's a z-score at 1.25. If we do p-norm, right, just with 1.25, it uses the defaults of 0 and 1 as the mean. So 1.25 gives you exactly the same answer as if you had told it the mean and standard deviation. And these commands in R, they like to have them in this order. So if you give it a number, it's going to think that's the number you're asking about, and then the next number is the mean, and the next number is the standard deviation. These things that are named, not that you would necessarily ever do this, right? But if you had that and you told it the standard deviation is 1.2 and the mean is 7.5, it will work that way as well, right? So the things that are in a default order, you can just give it the number. If you change the default orders, or there's certain options you're using that aren't necessarily standard ones, or you don't need to use all the time, if you name them, then it can do that. Q-norm gives you the quantiles or percentiles. Right? So if we say, what percentile would you be interested in? What's a low weight baby? What's the 5th percentile? Well, Q-norm, then you put the percentile you're interested in there, like 5%, and then mean, right, and standard deviation. And so 5.53 pounds would be the 5th percentile for a term baby, right? So we could check that, right? Did that give us the accurate answer? We could z-score this, right? 5.526 minus 7.5 divided by 1.2. That's a z-score negative 1.645. And so probability for a standard normal that you're less than 1.645 is about 5%. Right. Does that make sense, going back and forth? So another question that comes out of this, right, is about data set. Is it reasonable to use a model that says that these data are approximately normal, right? So, as an example, right, there's a bunch of data sets that are included with R. So if you just type data with these parentheses, it lists a bunch of data sets that are included with R on different topics. Some of these are taken as examples in different packages. There are different operations. They're used in some textbooks. So there's a whole bunch of these different things that are there. One data set is this, for instance, is this Nile. There's a data set on the flow of the Nile River. So these data sets have little health files. These are measurements of the annual flow of the River Nile at the Aswan Dam between 1871 and 1970, and 10 to the 8th cubic meters. It's a big river. So, it's actually a time series of length 100. So there's really more interest than just the values. But here are the values, all these different values of flow. Could you model the flow as a random, as coming from a normal distribution? Right? We could certainly do the mean of the Nile, the standard deviation of the Nile, right? But what's the shape, right? You can always look at the shape of the histogram, and so that's what it looks like. Right? Over time, sometimes it's up, sometimes it's down, but in this period, maybe that kind of looks normal. Right? So you can look at a histogram, but we can do another plot called a probability plot. Right? That is sort of useful for looking at these things. So, a probability plot is used, does do the data appear to be consistent with the normal shape. That is, if we want to do probability calculations, calculate percentiles, calculate probabilities in different areas, and we use the normal distribution, would it be reasonably accurate? Right? Maybe it's not going to be perfectly normal, but if it's pretty close, we're going to be accurate to 2, 3, maybe 4 decimal places, and so not be too terribly concerned. So so this kind of brings up the question, what, would the values from a normal sample look like? So if you had a bunch of values that did come from a normal, right? histogram should look like that. One thing you could think about though is if you put these values in order from smallest to largest, right? They'd be kind of spread out like a normal should be. So if we sort these in ascending order, the smallest one is called x with a 1 and kind of a parentheses. It's not the first observation you see, but it's the smallest one. And that would be less than the next sized one, less than or equal to the next sized one, etc. Up until we get the largest one. This one at this end is the minimum. And then this one up here is the maximum. And so when they put in order like this, these are called the order statistics. And so if you have n points, the lowest one should correspond to a certain percentile. Right? It's kind of 1 out of n, something like that, as the fraction of the data that should be at that point or less. Right? And then 2 out of n should be less than or equal to this one, and 3 out of n should be less than or equal to this one. So if you actually had a normal distribution with a certain mean and standard deviation, I could calculate the percentiles. Right? What values match up to every single percentile. So the expected percentile, I'm going to put this on the next page. We can look at the expected percentiles from a normal distribution with some sort of mean and standard deviation. So if we have, n points, right? You don't want to take n over n because that's 100%. You don't want to take 0 over n because that'd be 0. So what they suggest doing is taking how do the book do it exactly? There's a couple ways this is done, but let me match what's in the book. Right, oh, minus 0.5. Right, that's what it is. If you take 1 minus 0.5 over n, right, and let's multiply it by 100, look for that percentile from that distribution. That's the second one. Right? Take 2 minus 0.5 over n, like 1.5 over n, times 100 for the next percentile. Right? Down to n. So this one is n minus 0.5 over n, and that one is 100th percentile. So really it's taking these numbers 1 through n, and not going from 0, kind of avoiding the endpoints of 0 or 1, and just stepping off a little bit from that. Right? And so if n, for instance, is 100, then this is 1 minus 0.5 is 0.5 over 100. So times 100, which is that 5 over 100 times 100%. Wait, what do I want to do? That, times 100, so that's about the 0.5th percentile. That's pretty small, right? 0.5. And then the next one, so 1 minus 0.5 is 0.5. 2 minus 0.5 over 100 times that would be the 1.5th percentile. And going down, the top point would be the 99.5th percentile. So you get all these 100 points in there as different percentiles that would be typical of a normal. What we're going to do is graph those, plot those versus the actual order statistics that we get. Right. So I'll leave that up there. Before I write that up, let's write it the right way that R does this. All right. So here's with these. So if we sort the Nile values, right, we get those. Right? And there's a QQ norm function that's going to make this little plot for us, right, of Nile. So our sample values range from 456 up to 1370. So it puts them on this axis here. And then it puts the theoretical values in terms of the z-scores on this one. So if these values on this side were distributed, kind of spread out, spaced out, like they should be from a normal, this thing would be a straight line. A little subjective, saying how straight is it, or exactly. But this one, for the most part, is pretty straight, except for this point's a little bit low, or a little bit out of the pattern. Right. So you can't change the theoretical ones. You can change the data. So if this one had been a little higher, right, then it would be more in the straight line. So instead of having 456, one year with a particularly low flow of water, maybe drought conditions, right? If that one had been bigger, it would have kind of fit a little bit better with the normal pattern. At the upper end, this one, if it was a little bit lower maybe, but it's not too much off. This Nile is not too different from normal. And so that the normal quantile plot, this probability plot, is pretty close to straight. Right? There's another data set here called air quality. I think I'm going to attach it so we can help make things go a little quicker. This air quality data set has New York air quality measurements. They have a bunch of measurements in here, like ozone, solar, wind. So we could be concerned with the ozone measurements. Air quality, ozone, health of ozone. I want no histogram of ozone. Right? The ozone measurements don't look normal at all. Right? And they're mostly low. Within some days, there's a lot of sun and a lot of traffic, and you get a lot of surface ozone, which is bad for people. If you do that same plot, Q coordinate of that variable, you get more of a bend. Right? You can't really draw a straight line through these, right? It deviates. It's a bendy line, right? Instead of straight. So in these cases, the way you would make this thing look more normal is it needs a tail on the left. These things, you'd have to have some lower values to make this work out, or the ones up here would have to be scooted back in. So we're going to have to shift. And so in this picture, yeah, these things, these are too high. They'd have to be pulled down. Yes?
Do we have to, do we have to order them first, or can we just do the QQ norm?
You don't have to order them. It will do it for you. Yep. You put in the values, it puts them in order, it calculates the theoretical quantiles, and then shows you this picture. So with the normal, you can do things like do kind of a comparison. Does the probability distribution look like the data? You can do this for other arbitrary distributions in different ways. Primarily, we'll do it for a normal in this class kind of comparison. But anyway, so that's something on normal. We'll come back on Friday and do a little bit more with continuous distributions. Yeah.
On the test, will these be given, or do we have to copy these down on a sheet of paper?
No, so if I want to do normal calculations, I give you this.
Okay,
I only give you half of it.
Okay.
And make you use symmetry, but it's an easy thing to do if I want you to do those calculations. Yes.
Here's one of the pieces. The other one is on the video.
Okay, thank you. Yeah, yeah.
That's where I got from.
Yeah, it looks pretty durable.